So the chemical formula gives us information about the composition of a compound. For different applications, it can be helpful to know the mass percent composition, or just the mass percent. That's mean the same thing, it's just shorter. Mass percent of a particular element in the compound. So you've got this compound, it's got several elements in it, but there's one that you're interested in. So when we talk about a mass percent, we are using this general idea of percentage. It's helpful to keep this in mind. We'll use percentages in several different areas. Percent is the part that you're interested in divided by the whole thing times 100. So to find the mass percent of an element in a compound, what we'll do is we'll find the mass of the element that we're interested in and divide by the mass of the entire compound. Now, if they don't give you an amount of compound, what do? Well, the mass percent is an intensive property. It does not depend on the size of the sample. If something is 42% oxygen, no matter how big that sample is, it will be 42% oxygen. That's one of the useful things of percentages. So if we're just given a formula and asked to calculate the mass percent of oxygen, we can just choose what amount we're going to use. And if we can choose, we might as well choose something easy. And it's easy to choose 1 mole. So the reason this talks about the mass of element X in 1 mole is because that's really easy to find out. And the mass of 1 mole of the compound, that's just the molar mass of the compound. So there are two different sources that you can determine a mass percent from. One is the formula of the compound. The other is experimental mass analysis of the compound. You may take a sample of a compound and break it apart or decompose it in some way to separate out one of the elements and then get a mass of that. Then the mass of that individual element divided by the mass of the sample as a whole will give you the mass percent. So the basic idea of calculating mass percent is very similar, and yet the details of the steps that we go through are a little different depending on what kind we're looking at. So let's do this one. What's the mass percent of each element in water? What do we need first? We need the formula for water. What's the formula for water? H2O. H2O. So if we want the percent of hydrogen, then we're going to get, that's going to be the mass of hydrogen, that's the part we're interested in, divided by the whole thing, the mass of the water, times 100. Well, they didn't give us any masses, did they? So this is where we say, well, let's just choose a sample size. Let's just say 1 mole because it's easy. Well, what's the mass of hydrogen in 1 mole? How many moles of hydrogen are in 1 mole of water? 2. So 2 times the molar mass of hydrogen gives us 2.016 grams of hydrogen. What's the mass of 1 mole of water? 18.02. It's the mass of the hydrogen plus the mass of the oxygen. And so the calculator will actually show you 18.06 grams of water. So here we have the mass of water, here we have the mass of hydrogen. All we have to do is put them into our formula. So we've got 2.016 grams of hydrogen and 18.016 grams of water times 100. What unit does a percentage have? You could say it has no unit, or you could say it has the percent sign, right? But you see how this is grams over grams? Those are going to cancel out, basically. So a percentage is not going to have a unit like gram or kilogram or liter or anything like that. 2.016 divided by 18.016 times 100. %. I chose 4 significant figures there because we were using a molar mass with 4 significant figures. And here, when we did this one, the uncertain digit would be in the second place, which would also give it a 4 sig figs. So that's the percent of hydrogen. What's the quickest way to find the percent of oxygen? Subtract it from 100. The individual percentages of all the elements have to add up to 0. So if we take 100 and subtract 11.19, we're going to get 88.81. And that's the percent of oxygen. This would be hydrogen. Any questions? Mass percent can be used as a conversion factor because it relates the mass of one of the elements to the mass of the whole thing. And so when we're using percents this way, it helps to think of percent per cent. How many pennies in $1? 100. Percent literally means per 100. So when you're given a percentage, it means this many of the part per 100 of the whole. Here, Freon 112 is 69.58% chlorine. So we can make a very quick conversion factor, 69.58 grams of chlorine per 100 grams of the whole compound. It's not the only way to do these problems, but I think it's the most straightforward. So if you have another method that works well, go ahead. Okay, so what is the mass of hydrogen contained in 15.0 kilograms of water? What did we calculate in the previous example? The percent hydrogen in water, right? Percent hydrogen was, I believe, 11.19%, right? So that is equivalent to 11.19 grams of hydrogen per 100 grams of water. Well, this example has kilograms. We could also say that the percent hydrogen is equal to 11.19 kilograms of hydrogen per 100 kilograms of water. As long as the units of mass that we are putting in there are the same, it doesn't matter what unit we use. Because in the percent equation, they cancel out. And percent does not depend on size. Percent is the same. It's an intensive property, not extensive. So since we're given a mass of water in kilograms, let's make it easier on ourselves and make our conversion factor in kilograms. So what we're doing is we're starting with kilograms Yeah, that's a 0. 15.0 kilograms of water. And we're going to do this in one step. We're trying to find the mass of hydrogen, so that could be kilograms. Are they specifying what unit we have to use? No. Sometimes mastering chemistry makes you give it in a particular unit, and other times it doesn't care. It says just write the unit in, tell me what unit you're using. So we could use kilograms. And then down here, we're going to want kilograms of water. Again, we are using the units to tell us what to multiply and what to divide. A lot less thinking, if you ask me. So here's this relationship. We just need to make sure that we get it in there with the right thing on top. And the units tell us. Kilograms hydrogen is what needs to be on top. So 11.19 is with this unit. It needs to stay there. And 100 goes in the bottom. Now, because this is a percent, this 100 on the bottom is assumed to be exact. And the limit of significant figures comes in this number. So now we've got 15 times 11.19 divided by 100. Again, there are other ways of thinking about a problem like this, but we should all come up with the same answer. How many sig figs should I report in my answer? 3. So 1.68 kilograms of hydrogen. Problems like this tend to be fairly practical in nature. If you're mining iron and you have a particular kind of ore, you can do an analysis on some samples of the ore and find what percent by mass of iron is in this sample. And then if you need, a ton of iron, you can figure out how many tons of ore you would have to mine so that you could get the required amount of iron. So any questions about percentages? We can also get conversion factors from chemical formulas because they give us a relationship between numbers of atoms. So we look at this formula, C2Cl4F2. This gives us the relationship between numbers of carbon, chlorine, and fluorine atoms. So we can derive conversion factors. We could have 2 moles of carbon for every 1 mole of compound. We can have 4 moles of chlorine for every 1 mole of compound. And there are others. Now, it's important, these chemical formulas give relationships between amount in moles, or they could be done in terms of numbers of atoms and molecules, which is just not that useful. But this does not give us relationships of masses in grams. Okay? Does not give us masses. So determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. What's the first thing we need to figure out? We need the formula for aluminum sulfate. What kind of a compound is it? It's ionic. Aluminum is a metal. So we're going to have ions. We're going to have aluminum. What charge does aluminum ion have? 3 plus. We know that from the periodic table. And sulfate is? SO4, 2 minus. So when we combine those together, we get Al2, SO4, 3. Kind of messy, but that's what it is. There are a number of different ways you could go about solving this problem. I think what the publisher or the author intended was for us to use the chemical formula as a conversion factor. So what is the relationship between moles of this compound and moles of oxygen? "12 moles of oxygen per 1 mole of the compound." And that's just from the formula itself. We look in the formula, 3 times 4, 12. There's 12 oxygen atoms in a molecule or a formula unit. So there's 12 moles of oxygen in 1 mole of the compound. That's a useful relationship. Here we're starting with 7.2 grams of the compound. And they want mass of oxygen. So our path is going to be kind of crooked this time. We want grams of oxygen. We're going to need to do some moles in the middle, right? From grams of aluminum sulfate, we could calculate moles of what? Moles of aluminum sulfate. This relationship allows us to know moles of aluminum sulfate in relation to moles of oxygen. So from moles of aluminum sulfate, we could go to moles of oxygen. And from moles of oxygen, we could go to grams of oxygen. Everybody with me? So let's get this started here. 7.2. And yes, it's tedious to write all those letters and numbers. Just do it. We have 3 arrows. We're going to have 3 factors. And just like Dora, here's our path. Grams aluminum sulfate to moles of aluminum sulfate to moles of oxygen to grams of oxygen. That's what we put down here in the top. So we're starting with grams and we're going to moles. Oh, good grief. And then moles of oxygen. Thankfully that's a little shorter. And grams of oxygen. So then here we've got grams of aluminum sulfate. And down here we've got moles. And here we've got moles of oxygen. Always check and make sure that you got your units in the right place. And actually go through and cross them off. Which term is going to use this right here? Which term in my equation at the bottom are we going to use the 12 and the 1? The middle one, right? This guy? Moles of oxygen, moles of aluminum sulfate. So it was 12 moles of oxygen for 1 mole of aluminum sulfate. Where do we get the other numbers? Periodic table. The last one's the easiest because that's an element, so we can just look at oxygen on the periodic table, is 16. Aluminum sulfate, though, we got to calculate that. I'm going to do that way up here. 20. They're making those numbers smaller and smaller all the time, aren't they? Is it 9.8? Okay. So we've got 2 aluminums, 26.98. And how many sulfurs? 3. And what am I looking at? 12. Need that. 12 oxygens. And this is one of those calculations that you really should do twice because there's so many numbers. It's so easy to make a little mistake. I'm getting 342.17. Anybody else? Yeah. Okay, so that's going to go in this first term, 342.17. And yes, sometimes our calculations are a little messy. And if they get too messy, then we write them over again. But I can still read that. So 7.2 divided by 342.17 times 12 times 16. How many sig figs should my answer have? 2. Because the number that we're starting with is going to limit things. That is usually the case in problems and examples that you're given. Usually the starting number limits and not your conversion factors along the way. So this is going to be 4.0 grams of oxygen. Is that reasonable? Yeah, it is. Would 40 be reasonable? No, because how could you get 40 grams of oxygen in 7.2 grams of a compound, right? That doesn't work out. Questions?